Welcome, everyone. Today we are looking at Topic 7 in your SS3 Physics series, Nuclear Physics. This topic covers the structure of the nucleus, radioactivity, nuclear fission, nuclear fusion, and their applications. This topic is frequently tested in your examinations. You must understand the concepts, the equations, and the applications. Pay close attention. Let us begin. First, let me explain what nuclear physics is. Nuclear physics is the branch of physics that studies the nucleus of the atom. It deals with the structure, properties, and reactions of atomic nuclei. It also deals with the particles that make up the nucleus. These are protons and neutrons. They are collectively called nucleons. Nuclear physics is a fascinating field. It has many applications in energy, medicine, and technology. Understanding nuclear physics is essential for understanding the universe. It explains how stars produce energy. It explains how elements are formed. Let us now examine the structure of the nucleus in detail. Now let me explain the structure of the nucleus. The nucleus is the central part of an atom. It contains protons and neutrons. Protons are positively charged. Neutrons have no charge. The number of protons in the nucleus is called the atomic number. It is denoted by Z. The number of protons determines the element. The total number of protons and neutrons is called the mass number. It is denoted by A. The number of neutrons is equal to A minus Z. Nucleons are held together by the strong nuclear force. This force is much stronger than the electrostatic repulsion between protons. The nucleus is very small. It has a radius of about 10 to the power of negative 15 meters. Understanding the structure of the nucleus is essential for understanding nuclear reactions. This is the foundation of nuclear physics. Now, let me explain isotopes. Isotopes are atoms of the same element that have the same number of protons but different numbers of neutrons. They have the same atomic number but different mass numbers. For example, hydrogen has 3 isotopes: protium, deuterium, and tritium. Protium has 1 proton and no neutrons. Deuterium has 1 proton and 1 neutron. Tritium has 1 proton and 2 neutrons. Isotopes have similar chemical properties but different physical properties. Some isotopes are stable, others are radioactive. Radioactive isotopes are called radioisotopes. Understanding isotopes is essential for understanding nuclear reactions and applications. This is a key concept. Now let me explain radioactivity. Radioactivity is the spontaneous emission of radiation from the nucleus of an unstable atom. It was discovered by Henri Becquerel. It was studied by Marie and Pierre Curie. Radioactivity occurs because the nucleus has excess energy. It wants to become stable. It releases this energy by emitting radiation. There are 3 main types of radiation: alpha radiation, beta radiation, and gamma radiation. Understanding radioactivity is essential for understanding nuclear physics. This is a fundamental concept. Now let me explain the 3 types of radiation. The first type is alpha radiation. Alpha particles are helium nuclei. They consist of 2 protons and 2 neutrons. They have a charge of +2. They have a mass number of 4. Alpha particles are heavy and slow. They have low penetrating power. They can be stopped by a sheet of paper. They are highly ionizing. The second type is beta radiation. Beta particles are electrons. They are emitted from the nucleus when a neutron decays into a proton. They have a charge of -1. They have almost no mass. Beta particles are fast and light. They have moderate penetrating power. They can be stopped by a few millimeters of aluminum. They are moderately ionizing. The third type is gamma radiation. Gamma rays are electromagnetic waves. They have no charge and no mass. They have very high penetrating power. They can be stopped by several centimeters of lead or thick concrete. They are weakly ionizing. Understanding the 3 types of radiation is essential for understanding nuclear decay. This is frequently tested. Now let me explain nuclear decay equations. Nuclear decay equations represent the transformation of an unstable nucleus into a stable nucleus. In alpha decay, the nucleus emits an alpha particle. The atomic number decreases by 2. The mass number decreases by 4. The formula is X with mass number A, and atomic number Z decays to Y with mass number A minus 4 and atomic number Z minus 2, plus an alpha particle. In beta decay, the nucleus emits a beta particle. A neutron changes into a proton. The atomic number increases by 1. The mass number stays the same. The formula is X with mass number A and atomic number Z decays to Y with mass number A and atomic number Z plus 1 plus a beta particle. In gamma decay, the nucleus emits a gamma ray. There is no change in atomic number or mass number. The formula is X with mass number A and atomic number Z decays to X with mass number A and atomic number Z plus a gamma ray. Understanding these equations is essential for solving nuclear problems. This is a common calculation. Now, let me explain half-life. Half-life is the time required for half of the radioactive nuclei in a sample to decay. It is denoted by T subscript 1/2. Each radioactive isotope has a unique half-life. Some half-lives are very short, measured in microseconds. Some are very long, measured in billions of years. The half-life of carbon, 1,4, is 5,730 years. The half-life of uranium, 238, is 4.5 billion years. The half-life of radon, 222, is 3.8 days. The formula for half-life is N equals N naught times 1/2 to the power of T divided by T subscript 1/2. Here, N is the number of remaining nuclei. N naught is the initial number of nuclei. T is the time. T subscript 1/2 is the half-life. Understanding half-life is essential for understanding radioactive decay. This is a key concept. Now, let me explain nuclear fission. Nuclear fission is the splitting of a heavy nucleus into 2 lighter nuclei. It is accompanied by the release of a large amount of energy. Fission was discovered by Otto Hahn and Fritz Strassmann. It was explained by Lise Meitner and Otto Frisch. Fission occurs when a heavy nucleus, such as uranium 235, absorbs a neutron. The nucleus becomes unstable. It splits into 2 smaller nuclei. It also releases neutrons and energy. The formula is uranium 235 plus a neutron produces barium 141 and krypton 92 plus 3 neutrons plus energy. The energy released is about 200 million electron volts per fission. This energy is much larger than chemical energy. Fission is used in nuclear power plants and nuclear weapons. Understanding fission is essential for understanding nuclear energy. This is a frequently tested topic. Now, let me explain nuclear chain reaction. A nuclear chain reaction occurs when the neutrons released from fission cause further fission reactions. Each fission releases neutrons. These neutrons can cause other nuclei to undergo fission. This produces more neutrons. The reaction becomes self-sustaining. The chain reaction can be controlled or uncontrolled. In a controlled chain reaction, the number of neutrons is regulated. This is used in nuclear power plants. In an uncontrolled chain reaction, the number of neutrons increases rapidly. This is used in nuclear weapons. The critical mass is the minimum mass required for a chain reaction. Understanding chain reactions is essential for understanding nuclear reactors and weapons. This is a key concept. Now, let me explain nuclear fusion. Nuclear fusion is the joining of 2 light nuclei to form a heavier nucleus. It is accompanied by the release of a large amount of energy. Fusion is the process that powers the sun and other stars. In the sun, hydrogen nuclei fuse to form helium. The formula is 4 hydrogen nuclei fuse to form 1 helium nucleus plus energy. Fusion requires extremely high temperatures and pressures. This is called the thermonuclear process. Fusion releases more energy per unit mass than fission. Fusion is very difficult to achieve on Earth. It requires temperatures of millions of degrees. Scientists are working on controlled fusion. It would provide a clean and abundant source of energy. Understanding fusion is essential for understanding stellar energy. This is a key topic. Now let me explain the differences between fission and fusion. Fission is the splitting of heavy nuclei. Fusion is the joining of light nuclei. Fission releases energy from heavy elements. Fusion releases energy from light elements. Fission produces radioactive waste. Fusion produces little radioactive waste. Fission is easier to achieve. Fusion is very difficult to achieve. Fission is used in nuclear power plants. Fusion powers the sun. Fission can be controlled. Fusion is not yet controlled on Earth. Understanding these differences is essential for understanding nuclear energy. This is frequently tested in your examinations. Now let me explain the applications of nuclear physics. Nuclear physics has many applications. In energy, nuclear fission is used in nuclear power plants to generate electricity. In medicine, radioisotopes are used for diagnosis and treatment. X-rays and gamma rays are used for imaging. Radiation therapy is used to treat cancer. In industry, radioisotopes are used for quality control and tracing. In agriculture, radioisotopes are used for research and pest control. In carbon dating, carbon-14 is used to date archaeological remains. In nuclear weapons, fission and fusion are used for destructive purposes. Understanding the applications of nuclear physics is essential for understanding modern technology. This is a key topic. Now let me explain the importance of nuclear physics. Nuclear physics is important for several reasons. First, it provides a source of energy. Nuclear power plants produce a significant portion of the world's electricity. Second, it provides medical applications. Nuclear medicine saves lives. Third, it helps us understand the universe. It explains how stars produce energy. Fourth, it helps us understand the origin of elements. It explains how elements are formed in stars. Fifth, it provides industrial applications. It improves manufacturing and quality control. Sixth, it provides a tool for dating. Carbon dating helps us understand history. Understanding nuclear physics is essential for physics and technology. It is a fundamental part of modern science. Now let me explain the dangers of nuclear radiation. Nuclear radiation can be dangerous to living tissue. It can cause damage to cells and DNA. This can lead to cancer and genetic mutations. The severity of the damage depends on the type of radiation, the dose, and the duration of exposure. Alpha radiation is dangerous if ingested or inhaled. Beta radiation can damage the skin and eyes. Gamma radiation can penetrate the body and damage internal organs. It is important to use protective measures. These include shielding, distance, and time. Shielding involves using materials to block radiation. Distance involves keeping a safe distance from the source. Time involves limiting exposure time. Understanding the dangers of nuclear radiation is essential for safety. This is a key topic in health physics. Now, let me give you sample exam questions to prepare you for your test. What is nuclear physics? Nuclear physics is the branch of physics that studies the nucleus of the atom. What are isotopes? Isotopes are atoms of the same element with the same number of protons, but different numbers of neutrons. Define radioactivity. Radioactivity is the spontaneous emission of radiation from the nucleus of an unstable atom. State the three types of radiation: alpha radiation, beta radiation, and gamma radiation. Define half-life. Half-life is the time required for half of the radioactive nuclei in a sample to decay. Explain nuclear fission. Nuclear fission is the splitting of a heavy nucleus into two lighter nuclei. Explain nuclear fusion. Nuclear fusion is the joining of two light nuclei to form a heavier nucleus. State the differences between fission and fusion. Fission splits heavy nuclei. Fusion joins light nuclei. Fission produces radioactive waste. Fusion produces little waste. Let me summarize everything we have covered today. Nuclear physics studies the nucleus of the atom. The nucleus contains protons and neutrons. Isotopes have the same number of protons but different numbers of neutrons. Radioactivity is the spontaneous emission of radiation. The three types of radiation are alpha, beta, and gamma. Half-life is the time for half of the nuclei to decay. Nuclear fission splits heavy nuclei and releases energy. Nuclear fusion joins light nuclei and releases energy. Fission is used in nuclear power plants. Fusion powers the sun. Nuclear physics has many applications in energy, medicine, industry, and dating. Understanding nuclear physics is essential for physics and technology. This is Topic 7 in your SS3 Physics series. Study it well. It is frequently tested in your examinations. Well done.